So welcome back everybody to this session, this afternoon session. So the first speaker is an invited talk from Professor Valeria Molinero from the University of Utah. Thank you very much, Valeria, for accepting the invitation. So if you want to share your screen.
Yeah. Can you see my screen?
Yes, we can now.
Okay, thank you. Well, thank you, Paula, and thank you everyone for attending and for the invitation to present here. What I want to tell you about today is work we have done very recently that is towards understanding the mechanisms by which zeolites form. This work that has been sponsored by the Department of Energy of the US and has been done in collaboration between Devdas Tabal and Risa Bertolaso in my group at the University of Utah and Subo Banik and Subramanian Sankaranyan at the University of Illinois in Chicago. When we think about zeolites, we have to look at them and understand that these are just crystalline materials with ordered nanometer pores. These crystalline materials are made by arrangement of tetrahedra, and these tetrahedra are linked by the oxygens and center on the silicon, and the tetrahedra have a wide range of angles, so they can make multiple polymorphs. And actually, tetrahedra of silica are the ones that make all the phases of silica that exist. However, if we look at the phase diagram of silica, for example, we will not find zeolites there. We find multiple phases. Probably you're familiar with quartz, cristobalite, and the glass of silica, but there is no zeolites in the stable phase diagram. Nevertheless, the zeolites that are metastable crystals are synthesized at temperatures that are very close to ambient conditions. For example, up to 200 centigrades of temperature, and also they can stay after they have been formed and dehydrated for temperatures that run up to about 800 or 1000 centigrades. So these materials, despite being metastable, they're actually very common, and they're so common that they are the most used solid catalyst in the chemical industry. And although they are the most used solid catalyst in chemistry, the most prevalent use of zeolites is not in chemistry. If you look at this graph, you will see that the part that corresponds to the catalysis is very small. Most of the applications of zeolites are as absorbents, as detergent builders, and other applications that have to do with their ability to absorb molecules inside the pores. So, however, when we think about the structure of zeolites, the one that requires more control of the structure and connectivity of the pores and the sizes have to do with catalytic cracking and other chemical applications in which these materials are used to really get a specific organics, typically alkanes, and then do reactions that split them. Most of the industrial use of zeolites for catalysis is done in the oil industry. Now, when we think about what are these zeolites, there are many of them, and I'm going to show some examples before, but about a quarter of them are natural and all the others are synthetic. And the reason why there are so many synthetic zeolites is because there is a strong interest in the synthesis of zeolites that have controlled size and connectivity of the pores for chemical catalysis. Now, there are many zeolites already, about 260 polymorphs, out of which 50 are natural, and they have all these incredible shapes of pores that range from like almost 2 nanometers, well, 1.5 nanometers to 0.6 or 0.5 nanometers. Now, there are many possible zeolites with different pores, but this is a tiny fraction of the number of zeolites that have been proposed using molecular simulations or computer modeling. There are more than 300,000 proposed, and actually some people compute up to 2 million. So the question is why we cannot access these zeolites. Some of them clearly are high energy, but many of them are low energy, and they are supposed to be almost as stable as the zeolites that we have today, but they have not been accessed. And what people have concluded now through a lot of investigation is that the limitations in accessing these new polymorphs is mostly kinetic. It has to do with what is the pathway that you go from the reactants of zeolite synthesis to the final crystals. Now, the zeolites are synthesized not from the melt, but using a combination of organic cations that are typically tetralkyl ammonium cations. For example, here you see an example of tetrapropyl ammonium cation, and also in the presence of water. So these zeolites, what it has been proposed is that they are directed towards specific polymorphs by using cations that can orient inside the channels of the zeolites. So the prevailing idea is that the size and the shape of these cations that enters into the channels is what really templates the formation of the zeolites. But the question is, how do the channels form? So at which stage we have channels, and how does the crystallinity emerges in these materials? So at this point, the actual molecular mechanisms by which organic cations direct the crystallization of zeolites is not known. Part of the complication is that the formation of zeolites is a multi-stage process. And by this I mean that there are actually observable stages in experiments that start with a silica source, typically a tetraalkyl tetraorthosilicate that hydrolyzes in solution. And then you have also a structured dieting agent that are these cations. There's a water solution, there's a water that is also at pH that is very elevated. And then the silicates are going to start polymerizing, and these polymers are going to result in the formation of nanoparticles that are typically between 3 and 9 nanometers in size. And these nanoparticles, the structure of which is not very well understood, evolve towards the formation of crystalline zeolites that are detected in experiments at this stage when they are about a few nanometers, or when they're growing into large and well-developed materials by oriented attachment and monomer addition. So we have polymerization of silica, we have crystallization, we have oriented attachment. All of these processes are very complicated, and they involve multiple components. Despite the complications, actually, there have been a lot of advances in zeolite imaging and understanding what are the stages from almost nanoscopic perspective. So I'm showing here one example of a very recent paper from this year in which the authors perform a synthesis of zeolites in which you start with these tetrapropylammonium structured dieting agents, water, and silica source. And first you heat, and when you heat, the size of the particles that form is very small. Not much happens at 90 centigrades. Now, when you start heating to a larger temperature of about 400 Kelvin, what you see is that there are particles in solution, and these particles, according to cryo high-resolution TEM, they look amorphous and irregular. And then at later stages, what we can see is that these particles develop crystallinity, and eventually they start growing by oriented attachment. However, one of the challenges of these experiments is that it's not possible yet to image the formation of the zeolites in situ. So these are ex situ experiments, and that means that the particle we're seeing in the first picture does not correspond to the same particle as the second and the third. So we don't even have the statistics of this. So how do you go from the solution to the amorphous to the crystals? This is the question we want to answer. There's another thing that is interesting about the zeolite synthesis is that there is, in all the measurements that have been done for multiple zeolites, there are reports that the zeolites emerge in a way that looks like it's continuous. So what you have is that the particles form, and then if you follow the order by small angle scattering, X-ray scattering, or even by solubility, there is something that looks to be a continuous transformation from amorphous to zeolite when you have development of zeolitic order. Now, this is sort of strange because the formation of zeolite is a crystallization and it's a first-order transition. So what's happening in these transformations? At this point, the nature and the origin of this intermediate order is not known. So our goal in this project has been to understand the formation of the zeolites using molecular simulations. And this has many challenges. One of them is that the zeolite synthesis convolutes two types of rare events. One of them is the phase transition, the crystallization, and also we can say the phase segregation, because we start with the solution, then we go to aggregates, and then we go to crystals. So we have two phase transitions, but these transitions are mediated and happen through chemical reactions. And these chemical reactions are the ones that allow you to reform the zeolite network. If we consider silica without any water, you can only make it mobile above the glass transition at about 1200 centigrades. Now, the zeolites are synthesized at temperatures below 200 centigrades. So the way that you do have to really reform the silica-silica bonds is to have water and a very high pH to really enforce the condensation and hydrolysis of these bonds that is the prerequisite for the transformation of the network. However, there is one thing that is important and simplifies the picture. These chemical reactions can increase or decrease the rate of the transformation, And that's why changing the pH, you change the catalysis and the transformation goes lower. But they should be orthogonal to the coordinate for the transformation from amorphous to zeolite. So this zeolite formation coordinate, according to nucleation theory, and we have also done studies on that I'm not showing, is the size of the zeolite nucleus. And that means that what we have is a barrier that has to do with crystallization and is controlled with the interfacial tension of the zeolite and the driving force between liquid and zeolite. But you also have, on top of that, and perpendicular to the reaction coordinate, a very slow transformation, because every time you have to open and close a bond, you have to do a chemical reaction that has also a sizable chemical barrier. So the way we go to find the way to model in reasonable times the formation of the zeolite is to develop a very computationally efficient model that captures the relative stability of the phases, the thermodynamics of silica, zeolites versus liquid, but dismisses completely the barriers for the chemical reactions. The way we attain that is by using models that are extremely simplified. So at this level, we have modeled the hydrothermal synthesis with only 3 components. We have water, that is the solvent, but let me tell you that it's in a proportion that is extremely low. So we have about 1 silica every 20 water molecules and 1 structure-dating agent. So these are the typical conditions of synthesis. We have water that we model with a monatomic model MW, and this monatomic water model does not have hydrogen atoms, does not have electrostatics, and is nothing else than a silicon atom that has been reparametrized to look as water. And this model represents the interactions between water molecules as a combination of 2 body interactions that are short range, and they are soft, and a 3-body interaction that is just a cosine quadratic function that is repulsive of the angle. So if you have water, water, and water, and the angles are not 109, that is the one that we enter, then we have a repulsion. And this suffices to produce the thermodynamics and structures of water. Now, for the silica, initially in other stage, we modeled with something that was really water. But at this point, we have modeled silica also as a single particle, like water, that has tetrahedral interactions, but the interactions are not really having the single cosine angle of 109, but have a complex distribution of preferred angles that really match the distribution of angles in the zeolites. So we look at the zeolites, we compute the distribution of angles, and then we match that into a potential, and this potential is the one that you see here in blue, compared to the one for water that you see here in black. So we have the angular dependence for the TTT interaction, that is the silica, and then all the other interactions are 2-body. The structure-dating agent is a single particle that has 2-body interactions of a Stirlinger-Weber type with silica and with water, and the interaction between T and water we also consider to be a 2-body potential. So we parameterize the model in a way that is shamelessly simple, and nevertheless, we found that our model can reproduce very well the polymerization of silica. And for that, what we look at is the distribution in experiments above and in the simulations below of the speciation of silica particles, silica centers, as a function of the degree of condensation when the polymerization advances. Now, to read this, you have to see that Qi means a species of silica that has n silicon networks. So, for example, Q4 means that each silica is coordinated to other 4 silicas through the oxygens, and 3 with 3, and 2, and blah. So this means that we can reproduce the speciation of silica and the degree of condensation with a very simple model that does not have long-range interactions or even any chemistry. Now, when we look at the formation of the zeolites from the solution, we start from a solution in which we have the monomers of silica, we have water, and we have the structure-dating agents. And the proportions that we use are similar to the ones in the experiment, but let me tell you that this simulation that I'm showing now is at least 200 degrees higher than what you use in the hydrothermal synthesis of zeolites. Under these conditions, what we find is that there is a polymerization that also happens in the presence of the structure-dating agent. And these structure-dating agents, here shown in red and the silica shown in green, form nanoparticles. And these nanoparticles already have porosity that appears in the form of channels that evince themselves in a peak in the low-angle X-ray diffraction. I mention this because in the experiments, they have found this peak, but they have not been able to interpret what was the origin. We say that this peak that they find at low angle, what it is the distance between the channels in the amorphous zeolites, in the amorphous precursors. Now, when we look at the amorphous to zeolite transformation, that is a second stage, so first they form the nanoparticles and then they crystallize, you can see that if you just focus on the red, the channels look pretty similar. That's why the conditions and the X-ray don't show much change in this low region when you go from amorphous in blue to zeolite in red, although there are some other changes at high Q, not too much because the particles are very small. Nevertheless, when we look at only the silica particles, you can see clearly that in the initial particle is amorphous, and this is what we detect as amorphous in blue and what we detect as local order of the zeolite in green, but is essentially amorphous, while in the other case, you can see clearly the channels, and our codes have identified this system as a zeolite. Now, the pores in the amorphous and the zeolites are also quite similar, and this is consistent with what people saw in the experiments in the stages before and after crystallization. But we can say now why there are these pores. Importantly, at the conditions of synthesis that I'm showing here that are quite high temperature, the crystallization and polymerization are well-separated paths. So first polymerizes, second crystallizes. If we now go to temperatures that are consistent with the upper part of the zeolite synthesis, that is like 400 Kelvin or so, what we find is that the polymerization goes through oligomers, and these oligomers are the same as at high temperatures. I just didn't show them, and these oligomers are ordered, but eventually they form a particle that is almost glassy, actually is glassy. And you can see the glassiness in two things. First of all, in the fact that the particle does not have any spherical shape, so it's not a liquid. And actually, it's very difficult to relax the shape of this particle, even in microsecond simulations. Also, we know that this glassy particle has essentially the regular shape that people attribute to the amorphous precursors, also in the imaging of the zeolites. The other way to check that it's glassy is by the actual diffusion coefficients, and we found them to be extremely low. This should not be surprising because although 450 Kelvin is high for humans, it's low for silica. The glass transition temperature of silica without water and without everything is 1200 Kelvin, or no, 1400 Kelvin. And now, if we add water, the temperature of the glass transition for this condition should be very close to this value, even in the experiments, so it's even more in the simulations. So this particle is not only glassy, but already has some features. You can see here some of the large channels that are characteristics of the zeolite. So it's like you start to see some zeolitic features already in the glassy amorphous state. Another thing that I would like to mention is that the precursors of the zeolite, first of all, they depend on the water content, because the more dilute is the solution, and this doesn't look extremely dilute, but for zeolites, this is on the dilute side, they have more time to really accommodate and form more compact oligomers. And what you can see is that in these compact oligomers, you have a lot of what is called D4R, that is just cubes of silica. And these cubes of silica appear prominently in the oligomers, also in the experiments. But these cubes of silica are not part of the silica the zeolite we're forming. So this clearly shows that the precursors that we see in the oligomerization stage do not result directly in the crystal. So from that, we can conclude that the nucleation of zeolite from the solution to the condensed phase is not a classical mechanism. And that's why we have this intermediate step in which we have the amorphous aggregates. This has been discussed a lot in the zeolite community for about 20 years. Now, if we go more into the characterization of these silica nanoparticles that now contain the amorphous, the structure directing agent, what we can see is that the simulations produce a fraction of these QN species of silica that have the speciation of the number of silica neighbors, how condensed they are, that is in excellent agreement with the experiments. I'm showing here the experiment in blue and the simulations at 450 and 640 in green and pink. And what you can see is that the distribution is very similar, and actually the experiment is a little bit between the one that we see at 450 and 640. And this to us suggests that there may be a small degree of crystallinity already, as we see in the simulations at 450, but in the crystals, in the experiments at 400 Kelvin. I would like to emphasize that this idea that we have, that is a glassy, the system is glassy already at 400 Kelvin or so, is consistent with the experiments. To have an idea of the slowness of zeolite synthesis, although the glass transition should be at lower temperatures because of the longer accessible times in the experiments, if you want to synthesize a zeolite by hydrothermal synthesis at 300 Kelvin at room temperature, it takes about a year to synthesize the zeolites, and people weighted that and published the papers. Now, if you try to synthesize it at 400 Kelvin, it takes hours only. And in the simulations, we see this as glassy, but probably we are at the boundary of the glass transition under these conditions. So if these are the particles that form and the zeolite is not already in the initial particles that we see, why do we see that the transformation of the particles across their synthesis process looks like a continuous evolution between amorphous silica and zeolites? So experiments reflect this in structural and also in thermodynamic measures, that there is evolution in the structure and the thermodynamics before the crystals are detected. The question is, what is going on? Our interpretation of what's happening is that what we detect as an evolving intermediate really arises from a very slow crystallization within a glassy state. So for that, let me walk you through this phase diagram that we built as a function of the diameter of the silica particles. So I told you that the particles form by polymerization, and now we have these particles that are amorphous, and they're going to undergo the crystallization to zeolites. As a function of the size, the diameter of these amorphous nanoparticles, we computed the melting point of these aggregates in solution. So this is the melting line, the equilibrium melting line shown here in green. Then you can also come from above and take each of these aggregates and cool them down, and what you will find is that there's a temperature of maximum crystallization rate. This temperature of maximum crystallization rate is where there is a crossover between nucleation-dominated crystallization above, between Tm and Tx, and growth-dominated crystallization when you're going down. But finally, if we go down enough, and now I'm eyeballing this one because we don't have the glass transition, you will find the glass transition temperature. I'm here just using a heuristic relations of 2/3 of Tm is Tg. Now, this glass transition temperature, when you're approaching that point, the dynamics is extremely slow, and now the barriers also for nucleation, you're going so deep into the supercooled regime that the barriers for nucleation essentially become comparable or smaller than kT, and likewise, the driving force for crystal growth is extremely fast. So at these conditions of zeolite synthesis, what we find is that the particles are forming. Now we have to read the graph from the side. We are entering into this at constant temperature. We're growing the particles, and as they're growing, they're crossing into the zeolite region. And this zeolite region, they cross already very close to the glass transition. And when they're growing, they're essentially entering the glass transition line. So when they're getting to this point, what you see is that very, very slow dynamics of the diffusion, and that the nucleation and the growth are both dominated by the pre-exponents, that are the rate of attachment, that are the same as the diffusion time. So particles are producing a small nuclei everywhere. The nuclei are already supercritical, but they're growing extremely slowly. And this is why the first order transition looks like if it were a continuous transformation. Here you can see for the 6.5 nanometer nanoparticle that you have the transformation at 650 at 40 Kelvin. You get very good crystals at very short times, and the crystallinity here detected with green is very short range order, but you can see that even the outer part looks crystalline, although in blue indicates that it's not detected as crystalline. At 550 in between, it takes longer, but after 600 nanoseconds only, you have perfect crystals. And at 450, what you can see is that we identify pieces that look zeolitic with our order parameter, but the order is not long range. So what we have is this slow evolution, and now we have run much longer and they look a little bit better. But nevertheless, the characteristic channels of these zeolites already exist. So the final result I would like to share with you is the question of what is the smaller size of a zeolite that can be synthesized? And this is a question that is very current because people try to make smaller and smaller zeolites for catalysis, as they would have the best of the catalysis. I mean, they have the pores and they have the possibility of chemical reactions. However, they will not have the impediment of the transport between very long pores. So all the pores could be utilized. And there has been an effort to make smaller zeolites, and a recent paper just published 2 months ago shows that the smaller size that they would make was about 4 to 10 nanometers. Now the question is, what is the minimum size that is actually thermodynamically stable? And we can read back into this graph. Into this graph, you can read that as we make the zeolites smaller, what we're doing is we're crossing at a size of about 2.5, 3 nanometers, the actual temperatures of zeolite synthesis. So we can tell for sure that the zeolites will not be synthesized at sizes smaller than 3 nanometers because they're not even thermodynamically stable. Now, if we go to the actual question of the kinetics of formation, we have been able to form the zeolites spontaneously with 6 nanometers, 5, 4, 3 nanometer nanoparticles. But there is something interesting happening when we go to the smaller sizes of the nanoparticles. When we go to the smaller sizes, 3 nanometers, we can form the zeolites, but depending on the conditions, we have competing polymorphs. And these polymorphs actually are not crystals. They don't have periodic order. And this is not so surprising because these particles are very small. They don't need to have periodic order. They can have structures that are dominated by their interfaces. And for example, in this one, you can see that the center of the particle is actually 5-fold, and this 5-fold order is not extensible to 3D conditions. Most importantly, this order that appears actually is more stable than the zeolites themselves. So what we can say is that for these sizes that are extremely small, what you have is a competition between real solidic order and new polymorphs or small isomorphs that appear at this smaller size. And eventually you cannot form any more zeolites with controlled size of pores below these sizes. So I hope I convince you that we can do simulations with a very simple and computationally efficient model that provides molecular insights into multiple steps of zeolite synthesis. I show you a little bit about polymerization, a little bit about nucleation growth, and nothing about the oriented growth and attachment that we can also do with these models. But in summary, we can address with molecular simulations for the first time the hydrothermal synthesis of zeolites, and this because we developed a very simple, and is the first one ever that exists, model for hydrothermal synthesis of zeolites. And this is good for the phase transitions, polymerization, structure, and thermodynamics. And we attain this speed by having no reactions and having a coarse-grained representation. We find that the nucleation is non-classical. The oligomers in solution do not build the zeolite directly, but they polymerize into an amorphous state that then evolves. Nevertheless, these amorphous states have already the pores, and this may explain why people report amorphous zeolites in the literature, and they may be these truly amorphous zeolites. And the intermediate order seems to arise from a slow crystallization in a glass. And this is what really is the signature of the formation of these zeolites. And finally, that the size that is smaller is just 3 nanometers, that is pretty small and is close to the value recently attained in experiments. And with that, I would like to thank again my co-authors, particularly Dev Dastabal, that did almost all the work I'm showing here, Andres Abertolazo, and Subo Banik, and Subramanian Karanyan, and for your questions. I'm looking forward to it. Thank you.
Thank you very much, Valeria, for the very interesting and clear talk. So we have a time for a few questions. So the first question, okay, yes. So the first question is from Stephen Cox from the University of Cambridge. So very interesting. Have you tried annealing your glassy zeolites? If so, what structures do they form?
Yeah, hi, Steve. Yes, we do, and they form zeolites. So the ones that we find that they're glassy, like the 6 nanometers and even 4 or 5 nanometers, they go back to zeolites. The only regime where we see that the zeolites go to something else is when you go to very small sizes. This is not only in zeolites. We have a paper at the end of ICE 1 in which we show that also happens for ice. I mean, any crystal, when you get to very small sizes, the interfacial forces are going to dominate and make new polymorphs that are not periodic or isomers that are different from the bulk phase. But Steve, the ones that we anneal, they go very, very, very slowly to zeolites.
Okay. Thank you. Maybe I have a quick question, Valeria. So actually I had two, but the first one was, I wonder, so the picture you showed, it looked like that in the simulation box, you end up with one cluster, one zeolite all the time. Does it happen all the time that you end up with one single one?
So in our simulations, we have not an excess of structure-editing agent in the ones I show you. If you put an excess of structure-editing agent, what happens is that the structure-editing agent covers the surface of the zeolite, the nanoparticles, and they stop growing. Now, in the experiments, they can see these defined sizes that they get to a given size and they stop. Well, they don't stop, they continue aggregating, but very slowly. We don't find that in the simulations, and it probably the reason why there is not so much of a barrier for condensation is that we don't have charges that would prevent these particles from coalescing. So if we don't add an excess of a structure-editing agent, we don't find any significant barrier for the coalescence of the particles. But in the experiments, they do, and I think that is the electrostatics.
Okay. I have a very quick question about the pH. So you mentioned that the pH is critical, I guess, in experiments. So is it something, so I guess in experiment, do you know if they play around with pH, for example, to stop crystallization and reduce the sizes?
Absolutely. So this is a great point. So the pH needed for zeolite synthesis is about 10, 11. And actually doing the synthesis, the pH goes up because the reactions free more OH groups. But if you take at any stage and you cool it down to pH 3 or acidic or even neutral, you stop the crystallization. And that's the way that people have done amorphous zeolites. So you start with something that is evolving, and at one point you change the pH and you stop the transformation. And this is why I think that what they call amorphous zeolites are what we call these amorphous nanoparticles with the channels informed inside. But they still have a lot of catalytic activities, these amorphous zeolites.
All right.
Okay. There is one more question from Ian Robinson. Okay. You should be able to speak.
Yes, yeah, you can talk.
I don't have a microphone yet.
You're good.
You have.
Oh, there it is. Okay. Can you hear me now?
Yeah.
Hi. Thank you for a wonderful talk. That's really revealed a lot about zeolites to me. My question is a little bit facetious, and that is, why do we need crystals? Because it's usually said that you need the long-range transport of the tubes of the pores all the way through from on the outside to the inside of the crystal for them to be catalytic. But you showed that the amorphous phase is already continuous. It's got these.
I think this is a great question. Actually, the results, there are very few cases in which people have done what they call true amorphous zeolites, because everything at this scale looks amorphous in X-ray, but they're not, and they use IR to detect. And they also find catalytic activity and similar. Nevertheless, the catalytic activity of the real crystalline zeolites is slightly better. So the size of the pores and the catalytic activity are important in the amorphous zeolites, but the pores have higher selectivity in the case of the crystal. Nevertheless, it has been shown that, for example, these zeolites are selective from one hydrocarbon against the other, and the amorphous zeolites are also selective to them. So they can be used in the two cases. So it's a great point. And maybe at one point we can tell, we don't know to which extent the things that we call nano-zeolites are really crystalline, because the X-ray cannot tell us because of the size. And these results suggest that they're evolving towards crystallinity, but at the low temperatures of synthesis, they may end up in something that is quite distorted.
Yeah. Thank you.
Okay, fantastic. Thank you very much, Valeria, again.
Thank you, everyone.
So we can move on to the next speaker, who is Dimitrios Mathas from the University of Southampton.
Hello.
Hello, Dimitrios.
I just need to, okay, now I can present, all right?
Yeah. So okay.
So, can you see, oops, can you see the slide, the slide and the pointer?
Fantastic, yes.
All right. Thank you very much. Hello, everyone. My name is Dimitrios Mathas, and today I will talk about our research where we evaluate methods for calculating viscosity of lubricants at different operational conditions. I would like to thank the organizers of this very interesting conference and also for allowing me to give this talk. This is the outline of the presentation with the motivation of our work and the theory of molecular dynamics, such as equilibrium and non-equilibrium MD for calculating viscosity. This will be followed by our main results and conclusions, and then the current work we are doing. So why we're doing this? So there is a clear industrial interest in calculating the rheological properties of lubricants at different operational conditions by varying the temperature, the pressure, and the shear rate. And the main applications for this is the automotive industry and others, such as aerospace engineering. At times, it can be challenging and expensive to calculate those properties, and this is where computer simulations can offer a helping hand, while this kind of research also falls into the category of digitalization, which is a quite modern topic. So the basic theory behind molecular dynamics is that we follow the location of the particles, we perform time evolution, and we solve numerically the Newton's equation of motion. And because this is a many-body problem, and this equation cannot be solved analytically, we numerically integrate it. And for example, we update the positions and the velocities at each time step, which depend on the previous time step. And this figure here shows the example in MD for oscillations, for harmonic oscillations. Now, the main aspect of MD is the force field. And what is a force field? A force field is a mathematical function for the potential function which shows how the atoms interact with each other. And it consists of bonded and non-bonded terms. The bonded terms include bonds, angles between three atoms, and dihedrals between four atoms, while the non-bonded part includes the long-range pairwise interactions, the large zones, and the electrostatic Coulomb interaction. Now, the first method for calculating viscosity is the equilibrium MD, and the Green-Kubo method tells us that viscosity can be calculated by the integral of the autocorrelation function of the pressure tensor, and alpha beta is the Cartesian coordinates x, y, and z. V is the volume, the system's volume, and the autocorrelation is obtained by the ergodic hypothesis as a time average, which is equal to the ensemble average as well. And the value of the pressure tensor at its time step is calculated by this equation, which has an kinetic energy component and the force component. Tmax is the total simulation time, and T prime ideally goes up to infinity, and T means that we use a value at a later time of the simulation. Now for EMD, there are two layers of convergence, and the first one is the convergence of the autocorrelation function. So in MD, time is discretized, and we can denote the autocorrelation function with this C value here, which is calculated by this ensemble average. And S is an interval where we use the values of the pressure tensor, and P is the total number of correlations we have. D is a fraction of the simulation where we perform autocorrelation, and N is the index of the C values, and we have another couple of indexes for the sum. So as you can see in this example here for benzene, we obtain an autocorrelation function which decays to zero with a damped oscillation, and we want to integrate this function, which cannot be easy at higher pressures, for example. And as you can see, when we have a bigger correlation, this example here decays to zero, but it's not always the case. In this example, the function is oscillation is around 10 to the minus 7. The second layer of convergence is the value of zero shear viscosity, which is calculated by simple quadrature as shown here. This is the trapezoidal rule. And what we want is to acquire a viscosity which is time independent and is converged, as in this example of n-hexadecane, where after 40 nanoseconds we have a converged result. A second method for calculating viscosity is called non-equilibrium MD, and the idea is that we use perturbed equations of motion by using an external shear field. One algorithm that can be used, the slot algorithm, is very efficient for calculating viscosity, and it sets up a steady planar quet flow. We perform several simulations at different shear rates, and viscosity is given by its definition by dividing the pressure tensor and the shear rate. the CR rate is equal to the applied velocity at the top edge of the simulation box, and y is the box length at y dimension. And what we want to obtain is a figure similar like this, where there are two distinctive regions. The first region is the one where viscosity does not depend on the applied CR rate, the so-called Newtonian regime. And the second region, the CR thinning region, where there's a linear relationship between those two. Finally, we apply zero CR rate extrapolation for viscosity to acquire the Newtonian viscosity. This is an example of n-hexadecane where we scan a wide region for CR rates, and the x-axis is the logarithm of the applied CR rate, and y-axis is viscosity. So as we go to lower CR rates, we see that NEMD method has an increased standard deviation, and here we have 5 independent replicates for its blue data point. EMD is shown as orange circle, and the experimental value is red. So both methods do relatively well compared to experiment, and also running longer simulation improved the average viscosity and reduced the standard deviation. Here we saw an example of NEMD quiet flow using LAMPS, and this example is from our simulation of 159.10 dimethyl molecules. And we see that periodic boundary conditions are enforced in all 3 dimensions, and the slowed algorithm creates a linear velocity profile, as we can see here, that matches the changing box shape. And this is taken from our recent paper, which got published recently. Now, the software that we used is processing and simulation software. So for creating our initial structure, we used PacMol and MolTemplate, which are open source programs and are used to generate the topology files. And this is a Fortran code, and this is a Python code. And MolTemplate takes the output of PacMol and makes it LAMPS readable, and also allowing us to select the force field parameters. We use LAMPS, which is a classical molecular dynamics code that can be used for a number of simulations, and in our case, we used it for viscosity. We use the 9.10 dimethyl octadecane, which is a component of PO2 lubricant, and we calculated the 0 CR and CR viscosity at a range of pressure up to 1 gigapascal, while varying temperature from 40 to 150 Celsius, and CR rates from 10 to the power 6.5 to 10 to the power 8.5. We compared 2 methods, and also we compared against experiment. And we also tried 2 different force fields, the long optimized potential for liquid simulation and the GAF2 force field, the general Ampere force field. Both of them are all-atom force field, which means that they treat each atom explicitly, and they are more accurate than united atoms, but they're also more expensive in terms of computation. And we used roughly 10,000 atoms for simulation, and we used the starting point was a cube with a dimension of 65 angstrom, and the viscosity production run was equal to 40 nanoseconds for both methods. So first graph here, in the x-axis we have the logarithm of the applied CR rate, and on the y-axis the viscosity in log scale. And blue circles are results from LOPLS, and triangles are GAF force field result, and squares are experimental data. So at lower pressures, we achieve a Newtonian regime, and viscosity is calculated by an average over the Newtonian region, while at higher pressure, there is a CR thinning region, and we performed 0 CR rate extrapolation using a power layering equation. And overall, there was a good agreement between experiment and simulation. Additionally, we examined the pressure viscosity coefficient for our models, and on the x-axis we have the pressure range, and again viscosity on the y-axis. The orange data points are the equilibrium MD results, while NEMD is shown with green, and the gap to force field with yellow. So we see that at the point around 0.4, 0.5 to 0.5 gigapascal, the EMD method fails to calculate the accurate viscosity. And this is because the autocorrelation function that I showed you previously does not decay to zero, does not converge at that point. And this is because at higher pressures, the relaxation time increases. On the other hand, NEMD performs much better against experiment, which is shown with squares. And we conclude that NEMD simulation can capture high pressure viscosity, while EMD is known in literature as well that it's not very accurate at higher viscosities and pressure. So to conclude, we see that EMD is not ideal for viscous molecules, and this is because high relaxation times hinder the decay of the ACF. And also, viscosity simulations are computationally demanding. It's not a straightforward process. And NEMD simulation allow us to go at higher pressures, and we believe it's a reliable approach for calculating viscosity. Additionally, choosing an accurate force field is very important, which is parameterized for lubricants in our case. Currently, we perform confined NEMD simulations by using the LOPLS Southampton force field and a reactive force field called ReactFF. And now we have put our lubricant inside an iron oxide surface, which has been generated by this open source program here, LAMPS Builder, which has been developed by UN. And this open source code can be modified to include any lubricant between a number of surfaces. And now we investigate the different pressures that can be applied on the top region of the iron oxide, and here orange is the color of the iron that we apply the external force. And we also investigate the different film thicknesses and different shear speeds, and we can have a simulation. At this point, I would like to thank my supervisors from the University of Southampton, Professor Chris Kalaris, Professor Ling Wang, and Professor Walter Holpinger for useful discussions, and also the use of supercomputer facilities such as Iridis 5 from Southampton and Yang from the MMM Hub. I would like to thank our colleagues from Cepheler, and also Dr. Scott Bayer for providing us the experimental data of the lubricant from Georgia Institute of Technology. And finally, I would like to thank Dr. James Ewan from Imperial for useful discussions. Of course, I would like to thank all of you for your attention, and any questions, please let me know. Thank you very much.
Thank you very much, Dimitrios. Very nice talk. So there is one question from Otello Roscioni, but I also have a question, very quick one. So one of the ways that we, for example, use to reduce the problem of slow relaxation of the pressure tensor is to use the Einstein relationship, where rather than the autocorrelation function of the pressure, you use basically the velocities. Have you tried to, that should speed up a bit the convergence? I wonder if you have explored this.
Yeah, so I'm aware of there is the Einstein relation for viscosity as well. We didn't try this equation. We used the green Kubo in the first place, which was implemented in LAMPS. Although we then I rewrote the autocorrelation code with an in-house C code to experiment the convergence and the different autocorrelation parameters. But yes, this is another equation.
I was asking this because I wonder if in your non-equilibrium MD you see any crystallization when you start to shear it quite highly. But we don't know if happens.
I believe I've seen some graphs from other papers that suggest crystallization. I think the crystallization has also an influence on the viscosity. This can be seen from viscosity, but in our case, we didn't see the crystallization, and we had a shear thinning region at the higher shear rates.
Okay, thank you. Okay, so this here the question from Otello. Nice work and clear goal. Have you considered using united atom to describe the lubricant? This should reduce the relaxation time.
Right, thank you for your question. So we haven't tried the united atom, although some initial papers that I've read made they compared different available force field. for lubricants, and this paper from UN in 2016 made a comparison of different force fields, and the united atoms didn't perform very well for calculating the density as well, not only the viscosity. So we went straight forward to the all atom force field, especially the LOPLS, which is the one that's suggested for linear and branch hydrocarbons.